Hello, and thank you for joining me for this talk on population synthesis for delta Scuti stars, where I'll be talking about robust stellar parameters for A stars in general, and progressing that all the way through to an analysis of the multi-ridged period luminosity relation. So Rita already introduced delta Scuti stars earlier in this meeting, and this slide comes from her. One thing that everyone writes in the introduction to a paper on delta Scuti stars is some mass range, and I'm pretty convinced that we all just make it up on account of it's different in every single paper. So one of the things I'll actually present in this talk is a calculation of this mass range in a robust fashion. Rita described delta Scutis as p-mode and mixed mode pulsators. They can also pulsate in pure G modes, but not the kind that we see in gamma Dor stars, the kind instead that have very low radial orders, although in this talk I'll focus mainly on, in fact only on radial modes. They are often rapid rotators with a mean rotation velocity at the equator in excess of 100 kilometers per second, and they are often found in binary systems. The multiplicity fraction for A stars is about 0.7. And this is important because rapid rotators are systematically dimmer and cooler than their non-rotating counterparts. Here we have a non-rotating star in hydrostatic equilibrium, and we can see that the gravitational pressure and the radiation pressure are balanced. That is the definition of hydrostatic equilibrium. But for a rapid rotator, there is a difference. There's an additional term here in the effective gravity equation. And this centrifugal term goes as omega squared. And so the more rapidly rotating the star is, the more distorted it becomes. Now, this also means that you can get away with a lower radiative pressure in order to counteract gravity. So the nuclear luminosity of rapid rotators is lower. And since luminosity goes as r squared t to the 4, the luminosity is lower and the radius is bigger, therefore the temperature can be really markedly lower. In fact, it can be up to 1,000 Kelvin lower than a non-rotating star of the same mass and metallicity. And this affects the shape of the star, and it means that the viewing angle that we have to the star makes a difference for the observed temperature. This is a cool GIF that Anuj made for our recent paper. One thing that I would point out is that omega K and omega C are not the same thing. This is the critical rotation rate. This is the Keplerian rotation rate. The details of that you can find in our paper. But what I wanted to say about this slide is that from a polar viewpoint, the star is brighter, so the luminosity is higher, and the temperature decreases slightly. From an equatorial viewpoint, the star is much cooler, as I said, around 1,000 Kelvin for rapid rotators, and it can be dimmer. So in order to work out how these effects propagate through to our analysis of delta Scuti stars, we simulated over 1 million models using Anuj's grid as a base. We sampled each evolutionary track every megayear so that the stars are equally sampled in age. The masses are distributed according to a salpeter IMF. The metallicities have a solar neighborhood metallicity distribution. This comes from Willett et al. 2023. This doesn't mean that they all have solar metallicity. It's just that their distributions match the distribution of metallicities in the solar neighborhood. The rotation is drawn from observed distributions. Again, Dan Hay showed these distributions in his talk. They come from this series of papers. And binaries are simulated using known binary fractions from Stella Offner's paper, and also using known mass ratio distributions, which come from pulsation timing. So these physical processes can affect observational inference. So the processes in particular are rotation, binarity, and indeed measurement error, because we never measure anything with perfect precision. So the effect of rotation is generally to move stars to the right in this diagram. So each of these red arrows is one instantiation of our population synthesis model, so one of the 1 million models, and it's given a random rotation velocity from the distributions I described. And depending on whether you view that star from the equator or from the pole, it can move up a bit or down a bit, but generally they all move to the right. So that's a systematic effect. Binarity generally moves stars up, but it can also move stars to the right if the stars have a mass ratio very close to 1. Basically, these are unresolved binaries, and if you have photometry and you can't distinguish the two stars, you interpret them as a single star, then the temperature that you measure will be a weighted average, weighting by the luminosity of those two stellar temperatures. And then the measurement error is just plus or minus 250 Kelvin and some quantity in log L over L sun, which I think was 0.07 dex. If you add all these components up, what you see is that stars are systematically displaced in the HR diagram compared to non-rotating models. So the purple arrows here show all stars that get moved into our 1 sigma box. And by the way, this is the same box that I drew on these panels here. It's just that the aspect of the plot has changed a bit, so it's more like a rectangle now. But the purple are stars that get scattered in, and the red are the orange are the stars that get scattered out. This means there's quite a difference in stellar parameters of stars that you actually think are in the box from non-rotating models versus reality. And we can measure that. So with this population synthesis models that we've calculated, we can see that the distribution in masses is 45% wider. This is a sort of before and after of the two populations. So 45% wider in mass, and the age distribution looks very different indeed. Not only is it much broader, but it can also shift quite substantially, in this case by a few hundred megayears. The exact shift depends on where your 1 sigma box is located. So whether it's near the ZAMs, near the TAMs, or whatever. This also means that the masses and the ages that we get from isochrones are biased. This figure shows the change in age that you infer when you use isochrones to interpret models that we have synthesized. So this uses missed rotating isochrones, where the rotation is 40% of the critical rotation rate. So you can't get past this problem simply by using rotating isochrones. And the underestimations in age can actually exceed 100%. So if the true age is 75 megayears and you estimate that the age is 25 megayears, that gives you a 200% underestimation. If you ignore the stars at the ZAMs, then for the rest of this diagram, after the ZAMs, the age bias comes out to be about 30%. And on top of that bias, there is basically random scatter at the 0.1 solar mass and the 180 megayear level. So please be very careful when fitting the ages and masses of field stars using isochrones. In fact, it's probably better not to use them at all. And we have provided an applet called Rapid that you can use to infer stellar parameters instead. I'll give you a little talk through the GUI that we made. So here are all the controls where you can change the temperature and the luminosity and so on. The middle panel here is an HR diagram. This colored ellipsoid here is a 3 sigma ellipsoid, where the color scale indicates the weighting that we use for the synthetic models when we calculate the kernel density estimates in both mass and in age. So if I play this for you, you can drag this ellipsoid around, or you can scale the error bars manually, or you can type in the fields at the top to change the luminosity and the uncertainties. You can make these as asymmetric as you like, or you can make them symmetric if that's simply the data that you have. You click compute, and then it recalculates the mass and the age KDEs for you. And you can click make corner here, and it'll make you a corner plot. Now, we all know what corner plots look like. Here's one of the corner plots that you make. And the parameters that you get out by default look like this. And you can change those parameters using the applet. And so you can marginalize over the equatorial rotation rate or whatever you'd like to do in order to get your age, your mass, metallicity, whatever parameters you're interested in for your star. So what does this have to do with astroseismology? Well, we all use estimates of stellar properties, so we all want our inferred masses, inferred ages, or whatever to be as accurate as possible. So we all have an interest in having accurate properties. But if you really want to do some astroseismology, let's do it. I simulated some clusters. In particular, I simulated SEP-HER, on which I wrote a paper in 2024. The method here was to simulate this complex, because it's really a collection of associations, simulate this complex whose stars are known to have ages in this particular age range. I applied a narrow metal mass fraction prior, so it's the solar value plus or minus 0.001, so that's plus or minus about 8% or so. And then you compare the model delta news that you get out to the observed ones. So the observed ones are this green histogram here, and the model ones are the blue histogram. Now, the result is that there is no significant difference. If you calculate a two-sided KS test, the p-value is 0.011, so there's no significant difference in these populations. The differences that you can see come from a small bias in the observed delta nu method. We used the shell diagrams, which are more accurate than the autocorrelation method, but they're not perfect. If you want to know more, you could ask me about that in the discussion. And it's also because we had a crude age prior. So this was a uniform prior across this particular age range, whereas in fact, the complex is made up of multiple associations that have discrete ages within this range, and we sort of smoothed over that. So if you have a particular cluster you want me to simulate, please reach out. I'd be very happy to oblige. Moving on, instability strip boundaries. Let's suppose that every star inside the delta Scuti instability strip were pulsating. So that means they're all orange inside the instability strip. These are the pulsators, and all gray outside. These are the non-pulsators. Now this plot's very busy. So in this next one, we thin by a factor of 100. So only every 100th model is plotted. And now we're plotting their positions based on how we observe them. Now, equatorial inclinations are statistically more likely, and so the rotating stars are going to appear cooler. And you'll notice that a lot of these orange points have shifted beyond the red edge. Comparatively fewer have shifted beyond the blue edge. That's due to random measurement error and binaries. And now we're going to invert the problem. We're going to ask, where would the intrinsic instability strip boundaries have to be to match the observed boundaries? So the observed boundaries are these dashed black lines here, and the dashed blue and red lines are where the instability strip boundaries would have to be in order to match the pulsator fraction being 20% along these dashed black lines. So this is basically, it's a new basis for an intrinsic instability strip that will be of interest to modelers and observers alike. So what is the mass range of delta Scuti stars that I talked about on that first slide? Well, if you use the Dupré et al. Instability strip, that's this gray histogram, you'll get a mean mass of about 1.71 solar masses, and the intrinsic instability strip suggests a mean mass of about 1.81 solar masses. The 2 sigma interval, which contains 95% of the population, will have a mass in this range. And because the mean mass is now higher, the age of the average delta Scuti star gets revised down. Finally, onto the period luminosity relation. This is what the models predict. There is a gradient in temperature across the models and also a gradient in mass. Metallicity turns out to be pretty unimportant. A lot of people at this meeting have talked about a period density relation. We can calculate that too. It's extremely tight. These come from MESA models and Gyre mode frequencies. This is the expected behavior between pulsation period and density. And so if we rearrange this, then the exponent is -2. And since this is in log form, and if we fit a linear line to a log-log plot, we get that -2 here in the equation. This is also rotation invariant to 0th and 1st order. So that period luminosity relation, we can encapsulate with a convex hull, which is a curve that contains all of the points in the population with the least total area within the curve. And we can compare what that looks like for a non-rotating population or a population that has a realistic rotation distribution, and we see that it shifts. It shifts to the right because the star is less dense because of its oblate shape under rotation. We can also plot the inclination effects here, and this is now the green curve, and we'll see that the green curve is substantially broader than the orange curve, which turns out to be important. This here is the observed period luminosity relation with a second ridge. This is from Natasha Barak's paper. And if you plot the distance from the black line in the horizontal direction, you can make a histogram out of that. And this is the second ridge in the period luminosity relation that we would like to reproduce. And here's our attempt at that. The orange histogram here is our synthetic models where every star is presumed to pulsate in the fundamental mode only. This distribution includes binaries and rotation, but notice that it doesn't explain the second ridge. There's no orange peak here in the histogram for the second ridge, and so binaries cannot explain the second ridge. However, if we now make it so that 70% of stars pulsate in the fundamental radial mode and 30% pulsate in the n=5 mode, we now can explain that second ridge. It's important to note that the shape of this histogram depends on the population you observe. So if you take observations from Reed et al. 2024 instead, then you need a different mixture model of different pulsation modes in order to explain it. But I hope you'll agree that we do a pretty good job at reproducing those observations. So here are my conclusions. Thank you very much. The online audience watching this on YouTube, there is some bonus material. I have also simulated the delta nu distribution for field stars. This is the observed distribution from a paper that came out earlier this year. And this is my simulated distribution for field stars, where I assume that we can only measure delta nu if stars are younger than 33% of their main sequence lifetime. And if you compare these two histograms and line them up, you'll see we reproduce the observations incredibly well at the high delta nu end of the distribution. But what we don't capture are all of these stars down here on the left-hand side with very low delta nu values. I did experiment with changing this age limit, and it still doesn't give a satisfactory reproduction. And I think this is due to some observational bias or the fact that some stars just stop pulsating as they get older. That was something that Ian Berry mentioned in his talk earlier in the week. I also alluded to differences between Eshels and autocorrelations. So here is one example. For the same star, I calculate the Eshel diagram. The red points here are observed mode frequencies. The black points are model frequencies, and you will hopefully agree that we do a pretty good job at fitting those observed frequencies. And we get a delta nu value of 7.16. But if we use autocorrelation, then the best fitting value is 6.11 cycles per day, which is very different. Could we choose a different peak? Well, yes, but the next best peak is also not the correct one. And if we go into this range, then what we measure is half of delta mu and not the true delta mu. So really, shells do better than autocorrelation. Please don't think that I have cherry-picked this example. I could present these for days. Here's a different star. Again, our fit to the mode frequencies is very good. Delta nu comes out at 6.92, whereas the autocorrelation gives 6.03. And that's a very strong peak there. There are no other peaks that would give a reasonable value. It is important to get delta nu right. The Eshel method is the best one we have, but it is still fallible and there is still a small bias. If you want to know more, the paper will be submitted pretty soon. Thanks.